Welcome to Calculus. Today we will investigate how to write and solve differential equations. We'll take a look at three examples. Our first example is this word question. It says the rate of change of n is proportional to n. When t equals 0, n equals 250, and when t equals 1, n equals 400. Ultimately, we want to find what is the value of n when t equals 4. We want to start off by writing a differential equation to represent this scenario. We don't have a whole lot of details here, but from this first sentence, we can write a differential equation to represent these words, the rate of change of n. So that's where my differential is to begin. So as I write this equation, my differential is going to be dn dt. And that is representing the rate of change of n. Now, the second part of the sentence says it is proportional to n. Now, from Algebra 1, we know if we have a directly proportional relationship, the way that we can write that is as some constant k times the variable of, well, our independent variable, which here is n. So just by using that first sentence, I can write that differential equation dn dt equals k times n. Now, I have to use this differential equation to answer the question, what is the value of n when time equals 4? And that bumps us into really a solution process. So what I want to do is I want to move all my terms that involve the variable n to the left side. And I want to move anything that involves the variable t to the right side. So I'm just going to highlight what involves n. So definitely dn and also this n on the right side. Let me highlight what involves my t variable. In fact, I just have one factor there, the dt. I'm also going to include k. We'll group k with the dt. So essentially, I want to group, the way that I've color coded here, I want to group the green items on the left, the blue items on the right. So we can pretty quickly accomplish that. I'm going to divide the right side by n to cancel it there. And I'm going to divide the left side by n. I also know that I need to move this dt. So I'm going to do a simultaneous move here. I'm going to multiply the left side by dt to cancel. And dt is going to show up there on the right side. So by organizing and separating these variables, what we've got here on the left is now dn over just n equals k times dt. So that's grouped our variables and our differentials so that I've got only one type on each side. Once I've done this, what I want to do is actually integrate. I'm after a solution, so that would need to not be dn, the differential. I just want n, so I'm going to integrate that left side and the right side. And I see that on this left side, what I've got is essentially 1 over n times dn. So if I'm thinking about an antiderivative, the antiderivative for 1 over n dn is going to be the natural log of the absolute value of n. And that's how that left side is going to integrate. We'll go ahead and write that natural log of n. And that's going to equal, in fact, on this right side, I could write plus, let's call it c sub 1. And now we're ready to integrate the right side. So that side is just simply integration of k dt. So k, again, is just a constant, so that's going to just stay there. Integration of dt, if I think about antiderivative for dt, well, that's simply just t. So I'll include that, so it's going to be kt, and then a plus, we'll call that c2. So we're very close to having an equation that's usable. At this point, I want to get rid of the natural log. Ultimately, I want to get down to an equation where just n equals something in terms of t. So I can do a couple things here. What I'm going to do is, first of all, I'm going to consolidate my constants here. So I'm going to subtract c sub 1 from both sides. It'll cancel on the left. And then I got c sub 2 minus c sub 1 there on the right. So now I'm going to write natural log of absolute value of n equals kt plus, and what we'll call this is c sub 3. It's a constant. We don't know it, but it's the difference between c sub 2 and c sub 1. Now, to get from this point to an equation that involves n equals something, I need to, in a way, cancel the natural log. And so what I want to do is I want to, in a way, exponentiate. I want to take and raise e to the power of ln of natural log, natural log of absolute value of n. And I want to do the same thing to this right side, e to the power of kt plus c sub 3. Now, what does that do for us? Here on the left side, e to the power of ln of n is going to just result in n. So with that exponentiation, that really does it for us. And then on the right side, what I want to do is I want to split this into 1 e sub e to the power of kt, but then I want to split off this plus c sub 3. And just using my exponential rules, I can do so just by putting another base e to the power of c sub 3. So we're almost there to an equation. So let's bump this up to the next level just to save room there. So now I've got n equals, and I want to do a couple things here. I'm just going to note, first of all, that e to the power of c sub 3, that's a constant itself. E is a number, 2.71 about. C sub 3 is a constant. So what I'm going to call that is just c. And I'm going to put it out front as a constant coefficient. The only thing that's left here is e to the power of kt. And this equation, I want to go ahead and box it, is what we would call our exponential growth model. And we've seen this one pretty frequently in algebra. We saw it probably first in algebra 1, but it definitely follows us in algebra 2. And what we're seeing here in calculus is, where does it come from? It really comes from the integration and exponentiation of our original differential equation. One thing to note here, this c is my starting amount. Starting, and we'll just go ahead and put value. So we got our equation. At this point, what we need to do is use our information and the equation that we wrote to answer this question. So at this point, I'm looking at that second sentence. So we're told that when t equals 0, n equals 250. And essentially, that is a coordinate pair for us. So I'm just going to write that as 0, 250. And again, our independent variables t, dependent variables n. We also have another point here, 1, 400. And what we're looking for is, when t is 4, what is the value of n? Now, you might be looking at this and saying, well, we got some extra information. Why do I have these 2 points if I'm just trying to solve for an n value and I've already got an equation? Well, the short answer is I have 2 unknown constants. I got c, and I've also got k. So what I want to do first is I want to determine c, the starting value. And what we can do is you really just take my point that involves time 0, and I'm going to plug in 0 for t, and I'm going to plug in n value of 250. So let's see what that does for us. So we'll just plug in 250 for n equals c, and times e to the power of k times 0. And what we can see, first of all, is that this e to the power of k times 0 is going to be e to the power of 0, which will cancel as 1. So immediately I know c equals 250. And that's exactly as we kind of anticipated. Because I've got time 0, the starting amount should be 250, and our equation is supporting that. So I'm just going to fill in here, substitute 250 for c, e to the power of kt. Now I have a second unknown constant, k. So I do want to find that. Once I find that, then I can actually try to find my value of n when t equals 4. So for that one, I need to use my second point. Time 1 and value 400. So I'll make those substitutions just as we did with our starting value. Here I'll put 400 for n equals 250 e to the power of k times 1. So I want to solve for k here. So I'm going to start off by dividing by 250. And I'll cut off the zeros there, but let's just call it 40 over 25. In fact, we could probably reduce that down. 40 over 25 is going to, if I divide 5 out, it's going to reduce to 8 over 5. So let's go ahead and just reduce that, 8 over 5. And that's going to equal e to the power, k times 1 is just k. And so in a way, what I want to do now is I want to reverse exponentiate. I want to take the logarithm of both sides. In fact, I'm going to take the natural logarithm. My whole goal in doing that is to bring this k down out front. So using my laws of exponents, this equation's now going to be natural log of 8 over 5 equals k. And the natural log of e is just 1, so I don't need to really include that. So we're right here at the moment where we can actually solve our question. So we are looking for an n value. So what I'm going to do is, again, pick up my equation, kind of that intermediate one where I'd solved for c, and I'm going to plug in k. So n equals 250 e to the power, instead of k, I'm going to write power of natural log of 8/5. And I know there's a variable t there, but actually I want to just plug in 4 for t because that's my time. And that expression is going to give me my n value. So what I want to do is I want to just write that down and then take that to Desmos and calculate it. We'll head over there just now. So we'll type it in just like we wrote it. So it's the c value 250 times base e to the power of natural log of 8/5 times time of 4. And that's going to give us a value of 1,638.4. We'll take that back to finalize our answer. And our n value is going to be 1,638.4 when the time is 4. And that's our ultimate answer. So we'll give it a double box. So for our first question, really we practiced writing differential equation for that proportional setup. And what we got from it was this exponential growth model, n equals c times base e to the power of kt. Let's take a look at a second example. Our second example has some multiple parts. So we'll start with the part A. It says the number of bacteria in a culture is increasing according to the law of exponential growth. So one thing I can note is that's the equation that we just generated. So n equals c times e to the power of kt. We'll keep that in view. And what we know is this: there's 125 bacteria in the culture after 2 hours. So our n value is 125. In fact, our t value comes first. That's the independent variable. So 2 comma 125. And then we also know that after 4 hours, there's 350 bacteria. And our first task here is to find the initial population. So I want to take my exponential growth model, n equals c e to the power of kt, and I want to plug in as much as I know. What I'm looking for is ultimately this c value. That is the initial population. And so what I want to do is I want to take and plug in my first value. So we're just going to substitute in 2 for time and 125 for n. So we'll do that to begin. So I'm going to take 125, that's my n value, equals c times e to the power of k times 2. Now, once I've got that, I want to now solve for c. That's pretty easy to do. I'm just going to start by dividing by e to the power of, I'll put that in the order 2k. That'll cancel my base e. And I'll write e to the power of 2k. And what we get here is that c has the value of 125 over e to the power of 2k. Now what I want to do with that is make a substitution. So at this point, I'm going to pick up my equation again. But when I get to c, I'm going to put in what I just solved for. So n equals 125. In fact, what I want to do is write this with a negative power. So it's going to be 125 times e to the power of negative 2k times e to the power of kt. And that's looking good. So at this point, what I want to do is I want to use my second point, because really what I got to solve for is k. If I can find k, then I can actually come up with a value for c. So I'm going to take my second point. We'd already used the point 2, 125. So now I'm going to pick up 4, 350, and I'm going to plug those in. So that's going to be for us n value 350 equals 125. And I'm going to write this as e to the power. I see that I can really combine these powers by adding them. So negative 2k plus k times t, and I'm plugging in 4 for time, so 4k. So the next step would be 350 equals 125 e to the power of negative 2k plus 4k is 2k. So now I'm ready to solve for k. Let me bring that up here. So 350 equals 125 e to the power of 2k. So I'm going to start off, let's divide both sides by 125. And that gives us 350 over 125. We'll just leave that as it is, unreduced. So my next step is going to read 350 equals, 350 over 125 equals e to the power of 2k. And then to solve for k there, I'm going to take the natural log of both sides. And that'll bring that power 2k down as a coefficient. So my next step, and I'm going to clean up some of this notation just to give room there. We've used that already. So now what we see is that natural log of 350 over 125 equals 2k. The natural log of e is going to cancel. That's just 1. So to solve for k here, I just need to divide by 2 or multiply by half. And we'll go ahead and just cancel our 2. So k has the value of half times natural log of 350 over 125. So where I'm headed is back to our original expression for c. Remember, c is the initial value, and that's what we're trying to find. So C equals 125 over e to the power of 2k. At this point, all I got to do is plug in for k and evaluate. So let's do that. I'm going to pick up that expression. So it's 125 over e to the power of 2k. So k is this expression that we wrote right here. And I'm going to just plug it in. So it's 2 times half natural log 350 over 125. So lots of fractions here and powers. But let's get a value for that. That is C. We just want to get an estimate. So I'm going to write that down. It's 125 over 2 times half times natural log of 350 over 125. And again, we'll go to Desmos to get our estimate. So we'll type it in as we wrote it, 125 over e to the power of 2 times 1/2 times natural log of 350 over 125. And we're getting an estimate here that says 44.6. We'll round to the hundredth, 44.64. And we'll take that back to our note screen to finalize, 44.64. And we're just going to report that as bacteria. In fact, what we'll do is let's round this to the nearest bacteria. So we're going to say that there's 45 bacteria. And again, we just kind of got to keep in view, that's the number of bacteria at the very beginning of the experiment. So that solves part A for us. Let's take a look at part B. B says, write an exponential growth model for the bacteria population. So we kind of have been using that model already. We just really need to pick up our formula there. It's n equals c times e to the power of kt. And just thinking about the parts we would need to fill in to make this a good model, we would need to fill in the c, which we already found, and the k. So I'm just going to highlight those two parts. Let's go ahead and fill in our c values. So n right away equals 45 times e. And then at that point, we do need to come up with a value for k. But in fact, we already did. So really, it's just putting the pieces together. I'm going to highlight what we found for k. That's half times natural log of 350 over 125. What I'd like to do is just get a decimal for that. Typically, we round to 4 points after the decimal mark. So let's get an estimate. So we saw that from our part A, what we had calculated for k was half times natural log of 350 over 125. So that has the value of about 0.5148. We'll take it out 4 places. Once we got that, we can just plug it back into our formula. Go ahead and write here, this had about the value of 0.5148. So that's my k value. I'm going to plug it into my formula. And then t is our independent variable. So there's my model. A lot of the work had already been done in part A, finding the c and the k value. So now I want to use the model. We wrote the model in parts A and B. Now let's use it part C to actually write this. We want to use the model to determine the number of bacteria after 8 hours. So the nice thing once you have an equation like this is you just plug in your variable and calculate. So it's going to be 45 base E to the power of 0.5148 times, I'm looking for the number of bacteria after 8 hours, so times 8. So there's my expression. And again, once I write the expression, I want to use the calculator to evaluate. So again, we'll head over there. And let's take this to Desmos. So again, I'm going to type it in. 45 base E to the power, our K value is 0.5148. And I'm going to need parentheses times 8. And right away, we've got a value after 8 hours. We should have about 2,765.74. So again, if we were to round to the nearest bacteria, 2,766 bacteria. And again, a lot of the work was done in previous parts. So this is pretty quick to come up with these values. 2,760. We'll give our decimal. But what we would probably do is then say, 2,766 bacteria. So that's using the model if I know the time and I want to find the number of bacteria or items. Part D is flipping that around and saying, how many hours will it take for the bacteria to count to reach 25,000? Again, we can take our model, n equals c e to the power of kt. And again, I have the actual model here in part B. But there I'm going to plug in 25,000 for n. So 25,000 equals 45. It's my starting number. E to the power of 0.5148. I'm going to leave variable t because I'm solving for time. So I do want to solve for time. So I'll start by dividing by 45. Cancel on the right, show up on the left. So my next step, I'll have 25,000 over 45 equals E to the power of 0.5148 t. So again, we got to decide at that point, how do I get rid of E and bring down that power as a coefficient? Well, take natural log of both sides. It'll bring down the power, and we'll just let natural log set there on the left side. So now what we've got, let's just carry this up to preserve room. Natural log of this fraction 25,000 over 45 equals now 0.5148 t. And the natural log of E cancels as we've seen before because that's a value of 1. So to finalize my solution, I just need to divide by the K value, 0.5148. That leaves time by itself on the right. And our time value is going to come from this left expression, natural log of 25,000 over 45 divided by 0.5148. So one last time for this question to the calculator. And we'll type it in, natural log 25,000. Make sure I include parentheses. Divided by 45, all over that K value 0.5148. And that's going to give us about 12 point, we'll go ahead and round here actually to a decimal, 12.28 hours. So notice on that question, it's a lot of algebra. We didn't use any calculus. The calculus is behind the law of exponential growth. So we kind of have used what we did in the first question here, but notice we didn't do any integration, didn't involve any differential equations. let's give our estimate here. Time is about 12.28 hours. So that's for that law of exponential growth. And it's whenever you see an initial differential equation that is involving proportional relationship. Let's take a look at a different model. So our third example is about the law of heating and cooling. So what we want to say, let's go ahead and read this, but then we need to state Newton's law of cooling. And that'll give us another chance to use some calculus. So when an object is removed from a furnace and placed in an environment with a constant temperature of 80 degrees Fahrenheit, its core temperature is 1,500 degrees Fahrenheit. 1 hour after it is removed, the core temperature is 1,120 degrees Fahrenheit. We want to find the core temperature 5 hours after the object is removed from the furnace. Well, let's state our model. This is based on Newton's law of cooling. And what I want to do is initially just give the law of cooling in words, and then we'll translate it to a differential equation from the words. So what the words say is the rate of change of an object's temperature you can think that's my dt, the change of temperature over time, is proportional. So it varies proportionally. But there's a slight difference from our just plain proportional variation. It's the temperature is proportional to the difference. So I see an operation there, that's subtraction, to the difference between the object's temperature, and see if you can predict what we're going to take the difference between. So it's between the object's temperature itself and the temperature of the surrounding air or water. And the temperature, in fact, it could be anything. And the temperature, what we'll say, is of the surrounding environment. So there's Newton's law of cooling in words. What we want to do pretty much right away is convert this over to a differential equation. And so we can do so pretty easily just by translating the words. So I'm going to start the rate of change of an object's temperature. So the way I'm going to write that is the change in temperature dt, capital T, over d lowercase t time. That's the rate of change of an object's temperature. Is always an equal sign. Proportional tells me I got a k value. And if it's directly proportional like this, it's going to be k times. And the last thing that I need to catch is the difference between the object's temperature and the temperature of the surrounding environment. So that's going to be temperature of the object minus temperature of the surrounding environment. And that's our equation. So that's what we want to start with to actually create an equation for this example number 7. So what I want to start doing, first of all, is take our model here and just fill in the parts that I know. So I'm going to write dt, which I do not know much about yet, equals k times the temperature of the object, and I see that I know some stuff about that, but I'm going to leave it as a variable for now, minus the temperature of the surrounding environment. Now that is constant. I'm told in the words, it's a constant temperature of 80 degrees Fahrenheit. So for my equation, I'm actually going to plug in 80 for T sub S. Now I want to solve that. I've written the differential equation to represent the cooling situation. And again, like our previous question, like our first example in this lesson, I want to start off by organizing my like terms variables on each side. I want to separate my variables. So I'm going to highlight here the temperature and temperature minus 80. Those two terms need to be, in this case, on the left side. And then I want to also group, just like we did in our first example, the variables involving time. So I'll put K with that. So real similar to what we've done in that first example. So I'm going to start off, I'll cancel the blue T minus 80 by division here on the right side. And it'll stick over here on the left, T minus 80. And I'm going to cancel dt by multiplying, and it'll stick there on the right. So now what we've got is dt over t minus 80 equals k times dt. So that's looking good. At that point, we can integrate. I'll integrate both sides. On the left, that's going to turn into, again, I see that I've got 1 over t minus 80 times dt. So that's set up like natural logarithm. So if I'm looking for a antiderivative of 1 over t minus 80 dt, that's going to be natural log of absolute value t minus 80. But really on this one, I could probably drop the absolute value because everything in terms of our object is going to be greater than 80 degrees. Everything's cooling down. So I'm going to drop the absolute value there. So from the integration, our next step is going to be the natural log of t minus 80. And we'll go ahead and just put plus c sub 1 from the integration equals, on the right side, integration there's the same as our first example. If I've got k dt, the antiderivative is just going to be kt. So we'll put that there. In fact, let's keep it in green. kt plus c2. So we're kind of headed towards the same type of equation as we wrote in the first example. It'll look kind of similar to our exponential growth model. But let's get there. So I'm going to subtract c sub 1 just to combine our constants. So now I'm going to have natural log of t minus 80 equals kt. And then that difference again, c2 minus c1, we'll call c3. C sub 3. Same thing now. I want to exponentiate both sides. So I'm going to raise e to the power of the left side, natural log of t minus 80. Let's do the same there on the right side. So on the left, remember what comes of all that is just the power. In fact, the argument of the natural log is just going to turn into t minus 80 equals e to the power of kt times e to the power of c3. And again, what I'm going to call e to the power of c3 is just c. So at that point, I'm going to shrink down here so that I got enough room to write my equation here. So it's t minus 80 equals e to the, in fact, I'm going to move the c out front here, c e to the power of kt. So that's my equation. Took the same type steps. We started off with a differential equation and we separated the variables, integrated both sides, got down to where it was natural log, exponentiate, and at that point we've got a nice solution with just T for temperature and T for time. So let's kind of take a look again at the question. So initially, the core temperature is 1500 degrees Fahrenheit. So if I were to write that as a coordinate point, that'd be 0 for time, and temperature would be 1500. So let's go ahead and plug those in, because initially I want to find what's the good C value. So I'm going to plug in 1500 for temperature. So 1500 minus 80 equals C times e to the power of k times time here is 0. So we'll see something similar happen. This e to the power of k times 0 is going to disappear. C is 1500 minus 80. So just by doing that difference, I have a C value of 1420. So now I want to plug that in. I'm going to pick up my model again, and I'm going to write T. I'm going to move that 80 to the far side by addition. So 80 plus my C value 1420 e to the power of kt. So that was using that initial one. That helped me find C. So now what I want to find is the K value. I can use that second point to find the K value. So I'm looking here 1 hour. That's my time 1. After it's removed, the core temperature is 1120. So just like we had done with that first point, I want to plug that in now. So 1120 equals 80 plus 1420 e to the power of k times 1. And then I want to solve for k. So let's do so by subtracting 80. And 1120 minus 80 is going to give us 1040. Kind of running lean on space here, but we're right there at our terminus almost. So 1040 equals 1420e to the power of k. So definitely to get e to the power of k by itself, I'm going to divide by 1420. Cancels on the right, sticks on the left. And then I'm going to take natural log of both sides. So at that point, that's going to give me my value for k. So k is natural log of 1040 over 1420. Now, previous examples, we actually put that in the calculator, got a decimal. Another option that you can do is just leave it as an exact expression. So let's try that here. We're right at our question. Find the core temperature 5 hours after the object's removed from the furnace. So I'm going to pick up our model once more. I've kind of gone through many iterations of it to get to this point. But essentially, I'm going to pick up this nearly complete version and plug in natural log 1040 over 1420 for k. So here's our model kind of in its final form, because now I know all the constants. It's t equals 80 plus 1420 times e to the power of natural log. So this is our value for k of 1040 over 1420 times time. So that's my model. If I want to find the core temperature 5 hours after the object's removed, the only thing I need to substitute is 5 for time. So I'll make that substitution, and then all we have to do is calculate and get an estimate. So let's take that one last time to the calculator. And we'll find that temperature. So it's going to be, again, 80 plus 1420 times e to the power of natural log of 1040 over 1420, all times 5 hours. So what we're seeing is that given our model, according to Newton's law of cooling, after 5 hours, the temperature should be about 379.24 degrees Fahrenheit. And that gives us good opportunity to head back to our notes and finalize. Our final answer here is going to be, again, 379.24 degrees Fahrenheit. So two main models that we are taking from this lesson. The first one was just the kind of basic law of exponential growth. Second example here, Newton's law of cooling. Well, thank you for joining for this investigation of writing and solving differential equations. See you soon.